Okay, cool. So thank you very much for inviting me. And I'm Sofia Celi, and I'm a cryptography researcher at the company that was talked about, which is Brave. And Brave is well known for the browser, and we also have a VPN and other kind of services. But today I wanted to talk a little bit of some research that we have currently been making. I was also hoping that I could present you 2 upcoming papers that we have, but we found a bug, so that's not going to happen because that's always what happens with papers. But I'm going to at least talk to the first start of the system. We are indeed thinking of putting this in production. We still need to finish some things, but at least you will see a little bit of that. So I kind of aptly call these attestations over TLS 1.3 and CKP. And if you want to read at least the first part of this kind of like very complex distributed system that I'm going to be presenting, you're invited to read the specific link that is in this slide. And prior to people asking me, the protocol that I'm going to be introducing, it's called the Stefano. And the reason why it's called like that is because that's the name of a very famous football player that was Argentinian and was kind of exported to always have their career in Spain. And this follows the same name convention that we had in a protocol that is very famous and is kind of like the start of this research, which was called DECO. And DECO is aptly named by a football player who was Brazilian and all their life played in Portugal. So this is the idea of exporting one thing to another. And because I'm Latin American, I loved naming my protocols after football players. Okay, so let's go for the outline. So essentially what I'm going to be talking about today, as I told you, is essentially the design of a very complex and distributed system. What we want is to be able to attest certain specific kind of statements that exist at the data that is sent over the TLS. The reason why we chose TLS will be clear in the next slides, but in general, we wanted to design this system that usually comprehends of kind of like these 3 steps. The first step is that you have to have a way into actually how to commit to the specific data that is sent over the TLS layer. Then you also have to prove over zero knowledge that certain statements exist in those specific commitments. And for this, you have to actually show that that specific data conforms to a specific grammar. So in this case, that conforms to the HTML or the JSON grammar. And then prove, for example, by using some of the cipher suites that are used over TLS 1.3, which is usually AES in a GCM setting or Chachapoly. And lastly, on this specific presentation, I'm going to also give you some discussions of why at the browser level we're interested in these kind of protocols, because maybe that will be the most interesting thing for this crowd rather than me just presenting you again what zero knowledge proofs are. Okay, so again, on this talk, we're just going to be talking about the first point and the last point, and we will give you maybe some pointers to some of the future, but as I told you, that specific research is still ongoing. Okay, so what is the set the scene? Essentially what we want is that we want to have the ability to prove something. So why we want to do this is, for example, at the browser level, we want to actually attest if a specific user that is behind a client is a real human or is it a bot. This is a really complicated problem that I don't think is going to be completely solved with the introduction of this specific system, but at least it's going to give us the ability to generate certain signals that can actually tell us that indeed this specific user behind a client is a real human and is not a bot. So think, for example, to the fact that specifically when you send data over the TLS session, sometimes you send, for example, your bank statements, or you send your identity documents, or you send any other kind of statements that will be much more difficult for a bot or an automated agent to be able to forge or create, because they will need to go to a bank, they will need to issue a national identity, something like that. It is not impossible, because if you have enough financial resources or computational resources as a farm of a bot, you will be able also to emulate those signals, but at least it gives us a little bit of more like more true signals that we could use to detect fraud at the web case. Okay, so what do we have is that we want to have the ability to prove something, but obviously we don't want to actually send that and show that in the clear, because that will be a clear privacy violation. So what we decided instead is to rely on TLS that already has this data that is sent between clients and servers, and then prove via the usage of zero knowledge proof if a specific statements exist on that specific data that is sent at the TLS layer. Okay, so for example, let's say that I want to attest that indeed someone is truthfully a human and is really authorized to access a service because they are over 18. So what I will do is that I know that in that specific TLS traffic that is encrypted, I know that there's a plaintext representation of that traffic, and that the format that that specific plaintext representation follows is by using the HTML and JSON format. And because, for example, let's say that I'm targeting specifically the JSON format, I know that the JSON format has keys associated with values, and that then what I'm going to do is kind of like pass this specific statement, then find, for example, a specific key that has the value age, and whatever comes concatenated to that specific field age has to be an integer that has to be over 18. And the catch here is that you don't want to do this over the plaintext because that would be a privacy violation to show to whatever trusted party that a specific plaintext is clearly a privacy violation. So what we want to do is indeed to use zero knowledge proof to attest that indeed over this specific TLS session there was a specific statement that conforms to a specific JSON grammar, that in that specific JSON grammar there exists a field with the value age, and whatever is associated with that field that is the value age is an integer that is over 18. So as you see here, that's a very complex system, and today we're only going to be talking about the first part, which is how we generate commitments to this specific data that is sent over TLS, so later we could generate the zero knowledge proofs. And this is not something new. In fact, as I told you in some minutes ago, there's a very famous protocol that studied it all that is called DECO, the one that is named after the person that played the most in Portugal. Or sometimes you will see in the literature that they are also called three-party handshake protocols or CK-TLS protocols. What essentially they are is that they are modified TLS handshake so that from the view of the server, everything remains the same, but the client and the verifier are going to be secret sharing the session keys that are used in the TLS layer so that later the verifier kind of is forced to be able to commit to the data that is sent over that specific session. And as I told you, there are already many protocols that are doing that. For example, DECO, TLSNotary, OpenSteiner, TimeCrier, Garbled and Proof, Janus, and I think even like last week there was a protocol in ePrint about how to do this. So there's many research on this area. There are many active companies and different parties that are actively trying to deploy this kind of protocols. Oh, and it's empty. Okay, I don't know. Okay, but what happened with the state of the art is that currently some of the protocols that exist out there, they have some limitations that at least at the browser level we wanted to solve. So one of the biggest limitations is that if you read some of the previous literature, is that the majority of them are set up to only work with TLS 1.2. And here, as a standardization person, I will tell you that that's not probably a good idea, because indeed, even last year, the IETF in its TLS working group has decided to actually froze TLS 1.2, which means that no more features are going to be actually integrated into TLS 1.2, because the idea is to deprecate TLS 1.2 quite soon. So if you want to put anything that uses cryptography that relies on the TLS layer, the idea will always to be target TLS 1.3. In fact, the TLS working group at the IETF have decided that maybe we're going to have soon a new version of the protocol, because that will be incorporating post-quantum cryptography and also more privacy protections, as for example, the integration completely out of the box of encrypted client hello. What other limitations are there? Sometimes those protocols lack a formal security analysis. So something that you see if you read the paper is that at least in our protocol, we wanted to have a formal security analysis that was as close as possible to the formal security analysis that was performed for TLS 1.3 during the standardization process. We wanted to achieve the same properties that that protocol achieves. There were also some efficiency concerns because some of the algorithms that were used in some of those previous papers were a little slow or were not so optimized, because obviously in research, every time that you put an algorithm, then it turns out that there will be another paper that optimizes it. So we wanted to target the most optimized algorithms. They also didn't have any client privacy, and we will talk this later and it will be clear, so just keep it in like your mind. Right now I'm not going to be touching about it. And also they didn't have any open source implementations, and because we wanted to use that in the browser, we wanted to integrate it directly in the TLS library. So for example, in Boring SSL, which is the TLS library that is mostly used by the browsers. So we wanted to have at least a really solid implementation. And because of that, we introduced a protocol that we call the Stefan. Okay, so how does it work? Usually DCTLS protocols or CK-TLS protocols or three-party handshake protocols or whatever you want to call it follow kind of like this framework, which is essentially that you have three phases. You have a handshake phase, a query phase, and a commit phase. Something important to highlight here is that none of these phases actually happen sequentially, but at many places they are going to be happening in parallel. Why, for example, let's say that you want to start a TLS session. What you do is that you send a query, so that's kind of the query phase, essentially telling to the server, hey server, I'm a client, I want to initialize TLS session with you. And you send the client hello, so that's your query. And immediately because of that, you are starting the handshake phase as well. Later, when you receive the messages from the server, the replies from the server, essentially server hello, server certificate verifier, and server finished, essentially what you do is that you send that to the verifier, so the verifier kind of commits to those specific encrypted representation of the messages. So just with this like really easy description that I told you, as you see, all of these phases kind of happen sequentially and not really in parallel. So keep that in mind. Okay, so the first thing, why we decided to do for TLS 1.3, one of the things that you could easily ask me is like, oh, but like, is that really anything novel? Because if you have a protocol for TLS 1.2, it should be really easy to port it to TLS 1.3. And the truth is that it's not, because there's many differences between TLS 1.2 and TLS 1.3. Most notably, when the TLS working group at the IETF was standardizing TLS 1.3, they decided to have three important properties in mind. They wanted a protocol to have this higher security and stronger security assumptions. They want it to be as efficient as possible so that the server can immediately send application data at the first round of messages it sends. And they also wanted to have the majority of the handshake encrypted. So this is the description of TLS, like the very simple description, but essentially everything after server hello is encrypted. And there's also a difference between how you derive the keys. So in TLS 1.3, you will have a derivation of the key of some keys that are going to use in order to encrypt the handshake messages. And then you will have a different set of keys that are used in order to encrypt any record layer messages. So the keys that protect your handshake messages are different from the ones that you're going to be using when you send messages, the true messages from the client at the record layer phase. So migrating anything from TLS 1.2 is not just as easy as just changing the version. Indeed, it's even can be thought of a really different protocol. Okay, and yeah, and the division of the handshake is really easy. You have of the protocol is really easy. You have the handshake phase that essentially is done so you could authenticate to that specific server. So the server authenticates to the client, and you also have the derivation of the key, so you could use them to encrypt the messages. Okay, so the question will be, okay, this is a really lovely protocol. Now, how we integrate this third-party verifier so we can make this specific third party be able to commit to the messages that are sent or received in an encrypted form in the TLS layer. And the idea that Deco introduced is essentially that you're going to be adding this third party that we call the verifier, and the server is going to remain, or the view of the server is going to remain completely the same, while the client and the verifier are going to be secret sharing all of their keys between each other. And then what you have is kind of like a commit and proof system, in which essentially what you do is that you as a client receive those encrypted messages from the server, and you send them in an encrypted form to the verifier. So the verifier is committed to those specific messages. After you have those commitments, you can generate any kind of zero knowledge proofs that you want over those specific commitments. Okay, so as I told you, we have these specific three phases, and let's start looking maybe at the first phase, which is the handshake phase. Usually in TLS 1.3, the handshake phase is going to be having kind of three important properties. The first property is that somehow you want to achieve the generation of these specific secrets that is going to be used in order to encrypt the messages of the handshake and also to encrypt the messages of the record layer. So that is what happens in all of these HKDF calls that you see here, and it's also what happens when you send the client hello and the server hello. Later, there's other messages that we call the authentication messages, essentially the way that the server tells, hey, I'm the true server, and this is the true server that belongs to Google. I don't know, because I'm sending you the certificate that attests to my identity, and I'm also sending you a proof that indeed I hold the secret key associated to the public key in that certificate. And that's the certificate message and the certificate verified message. So you achieve authenticity via all of those messages, and then you also have a last message, which is the server finish, that essentially just provides integrity of the handshake. Okay, so when we are actually modifying them and adding this third party, which is the verifier, what we want essentially is to be able to remain with the same properties, but kind of look at those phases of the handshake to see how we do that. So essentially, as I told you, how do you start a TLS 1.3 handshake is that you as a client are going to be sending a message that we call the client hello. What does the client hello has? The client hello has an advertisement of all of the cipher suites that that specific client supports that can be used to encrypt and decrypt messages. It also has all of the signature algorithms that that specific client supports, and it also has all of the they call it key exchange algorithms that that specific client supports. And they send indeed a specific public key representation of that specific of those specific algorithms that have been advertised. Once the client hello is received by the server chooses one of each of those algorithms from that list, and with that the server actually decides which specific cipher suite is going to be used on that specific handshake. Okay, and that's the description on TLS 1.3. How we do it with the verifier is that instead of directly sending the client hello message, what we're going to do is that we're going to be generating additive shares of those specific parameters, so neither the client and the verifier have a full view of the key, but rather they just hold additive shares that in combinations are going to be used in order to generate the session keys that are going to encrypt the handshake messages and later also the record layer messages. Okay, and how do they actually perform all of these keys derivations is that because neither of them actually has a full view of that specific key, what they're going to be using is that they're going to be using a 2PC functionality. In general, what they're going to be using is a binary garbled circuit in order to derive all of these keys. So all of these operations that you see here in the general TLS 1.3 handshake happen only by the client, but here they're happening in a 2PC form, as you see here, so neither the client nor the verifier had the full view of those specific keys.
Sophia, can I ask a question?
Yes. Sorry.
Why do we need to chop the keys and why is this necessary?
Yes, so you will see in the next slide why it's necessary. But yeah, non-intuitively, this might seem that we're just doing some operations because we want. But later you will see what specifically we need this. So one of the things that I told you is that we want the verifier to be able to commit to those specific messages that are received by the client. One of the problems there is that if we just forward those encrypted messages to the client and allow the client to just decrypt those messages and see the plain text, then the client can easily modify those specific messages, generate an encryption of them, and send them to the verifier very happily. And we don't want that because it means that the client essentially can forge any message and then kind of trick the verifier into accepting them. So on the contrary, what we wanted is that the client receives those encrypted messages, forwards them to the verifier, and only when the verifier has received the encrypted representation of the messages, then they reveal their share of the key. So the client is not able to cheat anymore because they don't see the plaintext representation of the messages until they receive the share.
Thank you.
Yes. Yes, perfect. Oh, that's a great question. Okay, so that's essentially what we're doing. Essentially, once we derive all of these shares of the keys that are going to be used in order to encrypt the handshake messages, we receive all of the messages from the server, the authentication messages. So we receive server certificate verify, server client request certificate, I think it's called, I don't remember, and the server finished messages. You receive them in an encrypted form as a client. You are not able to decrypt them because you don't have the full view of the key, but you do forward them in an encrypted form to the verifier. Once the verifier has received them and has, in a way, committed to them, what they do is that then they reveal their share of the key so that the client can decrypt the messages and proceed as usually the TLS 1.3 handshake proceeds. Okay. And essentially one thing that also we needed to do is that at the beginning of the presentation, I told you that some of the early forms of these protocols didn't have client privacy. And the reason why they didn't have client privacy is because they indeed showed in the clear the proof that indeed the client is talking to the correct server. And you need actually the verifier to be able to see that you're talking to the correct server, so later it cannot be cheated that you were talking with an incorrect server or you're mounting your own server to talk to yourself. Usually, if you forward the certificate message to a third-party verifier, that incurs in a lot of privacy violations because over time what you're doing is that you're revealing the client browser history to this specific third-party that is the verifier. So we didn't want to do that, so what we did is what I called a ring signature zero-knowledge proof. So you can attest that you received a valid signature, but in relationship to a set of servers. So you cannot pinpoint out this signature belongs to this specific server, just that it was truthfully generated by a set of servers. So we cannot give by this kind of like a key anonymity assumptions over here. Okay, but just here, essentially, everything works the same. What you have is that you received as a client all of the messages in encrypted form. You forward them to the verifier. The verifier then is committed to those specific messages, and once that happens, they reveal that their specific share of that specific key so that the client can essentially decrypt. But here's a catch. So something that if you're familiar with is that I told you at the beginning that essentially what we wanted to work with was with the specific cipher suites that are used in the TLS 1.3 handshake and the TLS 1.3 protocol. But it turns out that those specific cipher suites are not committing. The cipher suites that are usually used in TLS 1.3 is AES GCM in an AAD setting. And if you're familiar with the literature, you will know that AES is in the GCM AAD setting. It's actually vulnerable to what is called a key committing attack. Essentially, what you can do is that you can find another key and another message, as you see here in the key prime and M prime, and essentially you're going to be kind of like colliding to the same cipher text. So essentially, you could find another message and trick the verifier that indeed this is a true encryption of that specific ciphertext when now you're actually encrypting to a different message. So we had to modify how AES works in the GCM AEAD setting, so this specific kind of like easy attack cannot be launched. And this is not only a theoretical attack, indeed this was attacked once at Amazon. They actually had this attack launched against them in their storage, I think. So what we did is that we don't only provide like the specific encryption representation of those specific plaintext that are sent as part of the TLS 1.3 handshake, but we also send a commitment to the share of the key that the client has, so that later it will be non-trivial or really easy for the client to find another key so they can launch this specific key committing attack. And again, to just bring home again what I told you, that essentially in these protocols, everything happens sequentially. As you see here, essentially we have this mechanism of the query. We receive the messages during the handshake phase, and we also are able to commit them kind of sequentially at the same time. And that's essentially it. So now what you have is that you have this ability of forwarding these specific messages to the verifier, using a cipher suite that now has really becoming a commitment scheme because we have prevented this key committing attack. And then you have the ability to actually generate any kind of zero knowledge proofs based on those specific commitments. And the client retains all of the possibilities that they usually have at the TLS 1.3 handshake, because once they receive their share of the key, they are able to decrypt the messages as they wish. And we indeed implemented this in Boring SSL directly because we are the Brave browser. So we essentially built over Creminium, and Creminium uses Boring SSL. So we implemented it directly in Boring SSL for around like 14K lines of code. And we also launched some LAN and WAN experiments. And what we find out is that our protocol is kind of very efficient because we end up in the handshake times that have less than 1 second, which is great because usually the timeout times that you have on TLS 1.3 are around 20 seconds. So we are like kind of like in that specific time frame. And we also have around like 80 kAB of communication complexity. Okay, but something that immediately people have asked me when I present this protocol is like, that is great. That seems like maybe a great way to actually generate these zero knowledge proofs over statements that are sent over the TLS session. But one of the problems is that you have to heavily modify the TLS stack. And if you don't have actual direct access to modifying this TLS stack, it will not be that possible to actually launch this protocol, because this indeed requires changes and heavy changes at the TLS level. And for security reasons, the majority of the browsers, but also of the CDNs and the servers, will not give you access on how to easily modify the TLS stack, because that will be a security concern. But because of that, and I've seen that sometimes in the community, some other parties would like to present or have the ability to generate these specific zero knowledge proofs, even though they are not a browser or they are not a CDN, and hence they don't have direct access to the stack. So I thought about some alternatives that you could use to also maybe launch this kind of zero knowledge proofs. Two that came to mind is RFC 9421, which is essentially what is called signed HTTP headers. So usually in a very distributed architecture, you will have a client that wants to talk with an origin server. In the middle of that distributed architecture, you're going to be having a CDN. So essentially what you do is that as a client, you say like, hey, I want to add these specific headers to my HTTP messages, and I don't want the CDN to remove them or to add any other HTTP headers, so that they when actually reach the origin server, they are exactly the same. So RFC 9421 introduces what it is called signing the HTTP headers and also the messages. So in a way, if you don't have access directly to generate these commitments on TLS, you can perhaps use the fact that there exists kind of like these signatures of the HTTP headers and also of the content to maybe generate some kind of, or to see them some kind of way as a commitment, so you could also generate zero-knowledge proofs. And in this way, you don't have to modify any of the TLS libraries because you're already relying on the fact that this is widely supported by the browsers and you don't need any modification. The other one that you can look at is by using something as JSON web signatures, where they also provide signatures over specific JSON blobs. So you could also use that in order to generate those zero-knowledge proofs. But just to note here, any of these kind of like specific ways to generate these signatures can be used to track users over multiple sites. So if you indeed want to do this, you have to do it very carefully so you don't end up with a privacy violation. Okay. So that is essentially, I give you like a little bit of an alternative, and now that you will be asking me, now that you have these specific commitments that can be generated by actually modifying the TLS handshake or maybe using the signed HTTP headers, what can I do with them? What you can do is that you can generate any kind of like zero-knowledge proof over them. They are really complicated zero-knowledge proofs because you have to prove many ways, many things. First, for example, that let's say that you have this specific JSON blob and you want to prove that indeed there exists this specific field that is called age, and whatever is the value associated to that specific key is an integer that is over 1 in this example. So essentially what you have to prove in zero knowledge is that this indeed conforms to the JSON grammar, that the field age is the only field with that specific value. It's unique in this specific JSON blob. And the specifically value that corresponds to that specific key is an integer and follows the rules for integers, and then also that specific value is bigger than 1. And this is not so simple, so indeed we have some upcoming work in just looking at the first step of this, which is indeed proving over zero-knowledge proofs that in a specific document conforms to a specific JSON or HTML grammar. And then what you would have to do is also prove that over AES, because that's the cipher sweep that we're currently using in TLS 1.3. So as you see here, this is not very easy, but essentially what you have is that you have the ability to prove any kind of a statement that you have over this specific TLS blob or specific JSON blob. Okay, so that is essentially what we did, and as you see here, as a conclusion, what we have done is the design of a very complex and distributed system. We have only made the first step, which is essentially modifying the TLS handshake so we can create those specific commitments. But the upcoming work is going to be looking at specifically how to build those specific zero-knowledge proofs. And here, more interesting perhaps to you is that you can ask me, maybe this is very interesting from some blockchain application, but why will be interesting for the web? Why are the browsers currently really interested in something like this? And the reason for this is because in the web we have a lot of fraud. So we had a lot of people actually launching bot farms against many services that are served over the web. And the fact is that the majority of the mechanisms that we have in order to attest if someone is a human or is a bot are quite limited. So we thought of maybe using the data that is sent over the TLS session in order to maybe generate better signals that can actually signal to us if indeed a user is a human or is not a human. One of the easy ways that you can actually catch bots is if you inject at the HTML layer what is called a honeypot field. A honeypot field is essentially a field that you don't display at the UI of the browser, but that bots are going to be filling up because they just like do this automatically. So they're just going to be filling it up. But it turns out that sometimes those specific honeypot fields will have some privacy considerations. So what we want is actually be able to parse this specific HTML that has been sent over the TLS session, and then check if the bot filled those specific fields by passing over zero-knowledge proofs, and then presented that specific proof. So someone can indeed say like, hey, I have done multiple times this specific proof, and they have presented to me many times this honeypot field. Hence, I have not filled them because I'm not a bot, and hence, please allow me to access other services because it has been verified that I'm not a bot. Furthermore, you can indeed like concatenate this idea of actually using honeypot fields with other ways that you can indeed attest if someone is a human or is a bot. Last week was the IETF in Bangkok, and one of the presentations that they presented was indeed an idea from the CDNs on how to actually catch bots. And one of the things that they realized is that there are some bots that are allowed, there are some bots that are not allowed. The ones that are allowed are, for example, an honest bot that tells you, hey, in your user agent, which is the first message that is sent after the TLS handshake, they're going to tell you, hey, I'm a true web crawler from Google. But that is really easy to forge, and it will allow you to access those services. But it's really easy to forge because that's literally just someone putting web crawler from Google, and there's no verification whatsoever. So one of the ideas that Cloudflare currently has is not only to check that indeed the user agent is set to the specific web crawler from Chrome, but also that they should present a certificate, a client certificate, attesting that indeed they come from Chrome, because they have a valid certificate in relationship with their claim that they comes from Chrome. Now, this is a madness to put in production, because if you have tried to actually request client certificates on the web, you will see that a lot of clients will immediately choke. They should not choke according to the standard of TLS 1.3, but there's a difference between what is assumed in the standard and what is actually happening in production. The majority of times, the browser will choke if indeed there's a request of the client certificate and the client does not have it. So instead of having this, we thought of, again, using something as the Stefano to actually attest that indeed this specific user has the correct user agent, and then just once that indeed they have presented a correct client certificate message, just present them and let them have some kind of code tokens. So now that another time that they want to access that specific service, they can leverage the fact that they have these zero knowledge proofs that attest that they have been honest in the past in order to be able to access that service. What else can we do?
Is this something that Cloudflare is doing?
Yeah. Not the Di Stefano. They just presented the easy version, which is just actually requesting the client certificate, but they were actually wondering if we could integrate together so we could do it. Yeah. It would be really cool if Cloudflare comes, because then we will also have it at the server CDN level.
Yes, of course.
Yeah. Okay. Another thing that people have been thinking about is that another way that you can catch someone to be a bot or not is, for example, by looking at the age of a device. And that, again, is usually sent in the user agent. Why is this important? Is because, for example, think that you are a malicious adversary and you want to create a bot farm. You're not going to be having really old devices or devices that are really old lying around. You rather just create, like, on the fly, these really cheap, simple devices that are really young. So one thing that you could always say is in your user agent how old that specific device has lived. And if it's a really young one, then you could know that this specific user is not a human, but rather is a bot. But again, if you all the time are revealing to a CDN or a specific verification system the device, the age of your device, that can incur, again, some privacy violations. So again, we thought that this could be a signal that we can attest by using something as Di Stefano or some kind of CK-TLS protocol in order to catch some users that are committing fraud. Okay, but here what I want to bring home is that while this might be a good solution or an interesting solution in which what we're creating is kind of like profiles of ideas of things that are sent over the TLS session that will allow us to maybe catch some bots, this is not the perfect solution, and I don't think there will be ever a perfect solution to actually catching some bots. Why? Because with much computational or financial power, anybody can create a bot that passes all of these checks. Anybody can create a bot that has bank statements. Anybody can create a bot that has identity documents, that has devices that are really old, that has a client certificate somehow also issued by Chrome. That actually happened in practice, that on some specific email services, some people managed to forge some certificates from Google Chrome. So anything is possible in the web. So this is just giving you some ability for your average bot that will not have all of the financial resources or computational resources to actually launch these kind of attacks. But at least it gives us the possibility of having more signals that we can attest at the TLS layer in order to catch malicious users. And that's why we're interested from the browser level. And as I told you, attesting fraud is never easy. And sometimes something that I have also heard of actually using these kind of systems in in the web is that sometimes they are planning to actually be used in order to, for example, generate some authorization mechanisms. So for example, if you're a user, you will have the ability to later access other services because it turns out that you have, for example, an account with Facebook, and you can leverage the fact that you have a correct reply that you have successfully authenticated with Facebook, and then use that to actually access other services. We're also interested that very heavily from the browser perspective, but we're a little bit concerned in that it could also create kind of like restrictive systems in which only certain users that have certain accounts with some certain account providers will have the ability to actually access other services. So just to bring home here, we're very interested from the browser perspective in both these kind of protocols, helping us to attest if a user is real or it's a bot, and also on the ability to maybe leverage these protocols in order to generate other kind of authentication and authorization mechanisms on other websites. And with that, I think I have really short time for questions, but yeah, thank you.
Thank you, Sofia. Now we have time for questions, especially because I also have one. But go ahead.
Thank you. I have a question of this kind. If we are talking about proof of humanity, we have a lot of bots who are useful and helpful. So how are we going to prove usefulness of other bots?
Usefulness of the bot?
No, how we are trying to find out that this is not a bot that we interact with, but we have bots that are useful. How are we going to expand this idea, whether they will be a human of a different kind of what?
Yeah. So in the case of the proposal of Cloudflare, when they are like authorized bots, because for example, those are real bots that are crawling the web and they really belong to Chrome, one of the ideas is that they present a certificate that has been correctly issued by their, by their company, and hence they can actually attest that they belong and that they are authorized to actually crawl the web. That could be one alternative, but it's true that in some cases, some fine-tuned signals have to be done, so we don't also prevent other bots that are there for crawling or for other really allowed cases.
It seems like there's a balance that you need to have between being useful to the servers and being useful to the clients, right?
Yeah.
So if I want to not crawl the web, but just have my OpenAI operator or my me, but not really me. I'm not there. I'm sleeping, but the AI does it for me. It's useful to me. But if you take the hat of the server or the service provider, they don't want me to do that.
Yeah.
So are you on their side or on my side?
Yeah. So this is becoming a debate question that we have sometimes at the W3C, which bots we consider to actually be honestly generated by companies and which are not. There's some ethical positioning in which they will say that no bot source should actually be allowed because it could be even a form of copyright violations or it could be against some frameworks. In general, what we have decided is okay, and I have some feelings about it from those at the W3C, is that if a bot belongs and is just crawling and belongs for a company that has for a long time shown that they are not malicious in their intent, that they are okay. But this is debatable.
But if it's not crawling in the general sense, but performing an action for a user, but it's just not a human, is that like good use, bad use, undecided?
Yeah, that depends. So usually the majority of websites will also signal to you via the robots file that you can load if you indeed are allowed to crawl or you are allowed to do any action. So in those cases, I think usually the decision is for whatever you have set up your website as.
So I had a great talk. I'd love to talk with you more about it. I had a quick question for this room. Do you think the majority of the research problems here are on make a better snark? Someone goes and does lettuce, tomato, fold, whatever. Or do you think they're on, okay, we have ZK proofs. What do we do? How do we solve these applications? Like which would you suggest is the direction to take?
So currently we're doing this research with actually parsing HTML and JSON, and it's really slow. So we really encourage people to actually keep working on some of those systems because the more that they actually increasing the research, like the better they are. On the web, usually the users will not wait at all for anything. So if you're thinking that, for example, your CK proof system will take 1 second, your users are going to hate it, for sure, at the web especially. Like, at least, for example, some people have been thinking of also using in some cases of search. And in search, if it's not of the millisecond, you will not be, your user is going to leave. So for the web and for the browsers, you need almost immediately that your system works. So the fastest, the greatest.
Hi, I've been using Brave for many years. I love it. As a human that is very bad at identifying motorcycles, what kind of non-intrusive ways to attest that you're not a bot and maybe a very bad at identifying motorcycle human have you researched? Because I would love to, be off of that burden of realizing that every time I want to use something.
Yes. So this is against CAPTCHAs, which I love. So CAPTCHAs are very painful for many people who have accessibility needs, or for many people from different cultural backgrounds. They will not be able to solve the CAPTCHAs sufficiently. Unfortunately, that is what we usually rely on the industry, but it's really bad. By introducing something like that, something like this, we're hoping to not have to rely on the CAPTCHA for these, but rather to have other signals that are generally sent of the TLS session in order to attest if you are a human or not. One interesting direction there is always this protocol that is called Privacy Pass that was standardized also by the ITF. They still rely on the CAPTCHA, but they rely on the fact that you only solve the CAPTCHA once, and then for like 100 times, you will just be providing a token that you can use immediately without having to solve the CAPTCHA. So something similar is in here that you could think of also of it as also as an anonymous credential, that you show that indeed you have these signals, and then the next times that you are like asked for solving a CAPTCHA, or asked to present an authorization mechanism, or asked to present something in order to access the service, then instead you just pop a token from your local storage and present that, which will be better for usability, quite frankly.
Thanks for the presentation. A question, as I understood that the whole flow of proving a statement over a content of a website requires anyway interaction with an online verifier, right? So, which thinking about some on-chain application, it's a bit unfortunate. What will it take to make the whole thing like completely non-interactive? So like, I don't know, I take the transcript of the conversation between the client and the server and I'm able to generate a ZKP out of it.
So what happens there is that once you have the TLS session and you have committed that to that specific verifier, the verifier has the commitments there. So later when you show that zero knowledge proof, you can indeed just use the fact that they are stick and like completely static at that point and generate whatever. One of the things that I have been thinking is that what you could also is expand the system so that once you have generated kind of like this zero knowledge proof that indeed attests that you are human, let's say it, then maybe you could create some kind of tokens so later the user can just pop from the storage, oh here, I already generated this zero knowledge proof, like I present that and I already did the computation in advance. Something like that could potentially work.
Thanks.
But I know nothing about on-chain, so I'm sorry.
What a heresy. In a conference on zero knowledge.
Sorry.
It's all good, it's all good. Thank you again for this talk.